Everyone thinks a whistling kettle is just boiling water. They're wrong. It's a precisely tuned instrument. That familiar high-pitched shriek, building from a low rumble to a piercing crescendo, it's a sound we associate with comfort, with morning tea, or a quiet evening brew. But what if I told you that sound isn't just steam escaping? It's a complex symphony of physics, pressure, and the very structure of the kettle itself. For centuries, humans have boiled water. From open fires with clay pots to the sleek electric models of today, the process has remained fundamentally the same. Yet, the whistle, that clever little invention, didn't truly emerge until much later, transforming a simple heating process into an audible alert. So how does this everyday marvel work? It begins, of course, with water heating up. As the water approaches its boiling point, small bubbles of steam start to form at the very bottom of the kettle, where the heat source is most intense. These bubbles are filled with water vapor, a gas. Initially, as they rise through the cooler water above, they collapse almost immediately, creating those tiny, barely audible clicks and rumbles you hear before a full boil. But as the water gets hotter and hotter, the entire body of water approaches 100 degrees Celsius or 212 degrees Fahrenheit. At this critical point, the steam bubbles no longer collapse. They grow larger and larger, rising to the surface, ready to escape. Now here's where the kettle's design becomes crucial. Most kettles have a spout, a simple opening for pouring. But a whistling kettle has a special cap or an integrated device at the end of that spout, often a small, two-holed mechanism. As the water boils, the steam builds up inside the kettle, creating pressure. This pressurized steam is then forced through the narrow opening of the whistle device. Think of it like a bottleneck, concentrating the flow. The magic, or rather, the physics, happens when the steam passes through the first hole of the whistle. This creates a fast-moving jet of steam. This jet then hits a second, slightly offset hole or a sharp edge within the whistle structure. This collision of the steam jet with the edge or second hole creates turbulence. It's a phenomenon known as a fluidic oscillator. The steam doesn't just flow through, it begins to oscillate or vibrate very rapidly. These rapid vibrations produce sound waves. The frequency of these sound waves, how fast they vibrate, determines the pitch of the whistle. A higher frequency means a higher, more piercing sound. The exact pitch and volume of the whistle are carefully engineered. They depend on the size and shape of the whistle's chambers, the diameter of the holes, and even the speed at which the steam is forced through. It's a tiny, complex wind instrument. Think of it like a flute or a recorder. You blow air across an edge, and the air column inside vibrates, creating a musical note. A kettle whistle works on a similar principle, but instead of breath, it uses the power of expanding steam. Early kettle whistles weren't always so refined. Some designs were simply a cap with a small hole, producing more of a hiss than a clear whistle. It took experimentation over decades to perfect the distinctive, attention-grabbing shriek we know today. The earliest known patent for a true whistling kettle-like device dates back to the late 19th century in the United States, around 1883, by a man named Richard Montgomery. His design aimed to create a steam alarm for various vessels, not just kettles. However, the modern, integrated kettle whistle likely evolved through various manufacturers and small innovations over time, becoming a common feature by the mid-20th century. It solved a real problem, forgetting the kettle on the stove. And that ultimately is the primary function of the whistle, safety and convenience. It prevents the kettle from boiling dry, potentially damaging it, or, in extreme cases, causing a fire. It's a simple, yet incredibly effective alarm system. Next time you hear that familiar sound, don't just think of boiling water. Appreciate the intricate dance of steam and pressure, the carefully engineered acoustics, and the history of innovation that brings a little symphony to your daily routine. It's a beautiful example of how everyday objects, when we look a little closer, reveal layers of fascinating physics and clever design. A reminder that even the simplest sounds can hold profound scientific stories. What other everyday sounds are secretly scientific marvels?